Hello everyone, you're welcome to this channel once again. Today we have a question bordering a propeller driven aircraft and how to calculate the power required. Now let's read to the question we have today. Consider a propeller driven airplane with the following parameters. The wing area S equals 16 meters squared. The wingspan B equals 11 meters. And the weight 9 kilonewton. The zero lift drag coefficient CDO equals 0.04. The Oswald efficiency factor E is 0.78. Now, calculate the aircraft power required at low altitude. Where the air density rho equals 1.2 kilogram meter cube. To perform a straight and unaccelerated climb at the climb angle gamma equals 25 degrees and the velocity v stream equals 30 meters per second. Ignore the aerodynamic losses of the propeller. That is, we are supposed to ignore other losses due to aerodynamic inadequacy from the propeller. Now, let's pull out the parameters one by one. We have a propeller driven aircraft. We have the wing area 16 meter cube. We have the wingspan B 11 meters. We have the weight given 9 Newton. We have the zero lift coefficient drag CDU 0.04. We have the Oswald efficiency factor E, which is 0.78. And we are asked to calculate the power required for the aircraft. We were given the density, which is a sea level density, which is 1.2 kilogram meter cube. And we have the climb angle given 25 degree. And we have the main velocity of the aircraft, which is 30 meters per second. Now we are assumed to ignore other losses from the propeller. Don't let us forget that using the 2SB, we can calculate the aspect ratio for the aircraft, which is B squared over S. That gives us 11 squared over 16, which is 7.56. That's the aspect ratio calculator. Now, using the aircraft flight dynamics schematic, which we can generate the thrust, the weight, the drag, and the lift. So this is the lift. The thrust is going this way, the thrust of the aircraft, and the weight of the aircraft, and the dragging force moving this way. Now from here we can deduce that the angle subtended here is a fly path angle, which is perpendicular to the thrust. Now we can deduce that for this particular straight level on accelerated flight, that our lift, which is air, is going to be equal, the lift is going to be equal to weight cos gamma, which is a flight angle. So for our lift here to be equal to the weight multiplied by cos gamma, then we can deduce that if lift equation give us half rho s v square cl, then cl equals 2l rho s v square. So therefore our cl equals 2 cos gamma w over rho s v gamma squared. So therefore, by slotting all our value here into our deduced equation, we have our CL to be 2 multiplied by cos 25 multiplied by, what's the weight? 9,000 all over 1.2 times 16 times 30. That gives us 0.9441, which is the coefficient of lift. Now we can also deduce that our CD equals CDO using the coefficient of drag equation, CDO plus CL squared over pi EAR. That gives us our CDO, which is 0.04 plus also our CL 0.9441 squared over 3.14 times was our E, 0.78 times, and our aspect ratio 7.56. That gives us 0.0881. Now that we have found the true value, which is a CDO, CDL, now let's find the dragging force. So drag equals half rho s v square CD. So our drag becomes half multiplied by 1.2, 16, 30 squared, 0.0881. So therefore the drag becomes 761.17 Newton. That's the drag force which the aircraft is experiencing during the flight. Now, you can use the thrust formula, which is D plus W sine gamma from the schematic of the flight diagram. So that gives us our thrust to be 761.17 plus what was the weight? 9,000 sine 25. So therefore, our calculated thrust give us 4,564.73 Newton. Now don't let us forget that the power required equation, which is the thrust multiplied by the velocity, that is the product of the thrust to the velocity, it gives us the thrust 4,564.73 multiplied by the velocity, which is 30 meters per second. So our required power calculated becomes 136.94 kilowatts. Thank you very much for staying tuned.